Hi guys, welcome back to the final video in the series of videos about Chapter 5 Forces and Motion. In the previous video you learned how to calculate the resultant force using Newton's second law of motion. And if you've not yet seen that video, I suggest you do that now, and you can use the link that pops up now. In this final video we will take a look at braking and collisions. As usual, let's review today's learning goals. After this lesson, you will be able to explain what we mean by negative acceleration. You'll be able to explain reaction time and distance and how they are related, and you'll be able to determine the reaction distance, the braking distance, and the stopping distance using a velocity time graph. Let's take a look at an example first. This diagram shows us the velocity time graph of a braking car. In 4 seconds, the car comes to a complete stop. Its speed has decreased from 72 km per hour to 0 km per hour. Remember, the gradient in a velocity time graph gives us the acceleration, so let's determine the gradient. And, as always, let's convert the speed to meters per second first by dividing the 72 by 3.6. Doing so gives us v1, which is equal to 20 meters per second. And obviously 0 km per hour is equal to 0 meters per second. The acceleration is equal to the change in speed, delta v, divided by the time duration, delta t. When we use these numbers for v1, v2, t1 and t2, we get the following. 0 minus 20 divided by 4.0 minus 0, which is equal to minus 5.0 meters per second squared. And as you can see, the acceleration is smaller than 0. It is negative. A negative acceleration is also called deceleration, as you may have guessed. In one of the previous videos, you learned how to determine the distance traveled from a velocity time graph. Do you still know how to do that? Well, let's find out. Remember, in a velocity time graph, you can figure out the distance traveled by determining the area underneath the graph. In this case, the area is the area of this triangle. And, as you may know, the area of a triangle is equal to 1/2 times the base times the height of the triangle. Here, the area is equal to 1/2 times 4.0 times 20, which is equal to 40 meters. So, the braking distance of the car is equal to 40 meters. However, when it comes to collisions, or rather, avoiding collisions, there's one more very important factor, and that is reaction time. Let's have a look at reaction time and how it influences the total distance before the car comes to a full stop. Imagine driving your car, listening to music, maybe checking some messages, though you know you shouldn't, when all of a sudden a chicken crosses the road. What do? As soon as you see the chicken, you start to brake, right? Well, wrong, because it takes a little bit of time for your brain to register what happened and tell your foot to hit the brake. So, let's hit the brake. But how? Well, maybe pause the video. You should really pause the video. Do it now. Okay, so hopefully you unpaused the video. Well, if not, you wouldn't be hearing me right now. So, let's take a look at the timestamp you wrote down. Did you write it down? Well, I hope you did. Now let's calculate your reaction time, and you can do this by taking the difference between the timestamp you wrote down and the timestamp when I first told you to pause the video, which was roughly 3.5 minutes into the video. What was your reaction time? Well, not bad, at least I hope. Why is reaction time important in traffic anyway? Well, reaction time is important because it determines the distance your car travels before you start braking. In other words, your car will not slow down before you react. Let's take a look at an example. So, imagine driving your car when all of a sudden there's a chicken in the road. Again, during the time it takes to react, your car will travel a certain distance. And this is called the reaction distance. Then, you start braking and your car will come to a stop. And this distance is called the braking distance. The total distance is called the stopping distance. which in this case is the sum of the reaction distance and the braking distance. Let's take another look at the same example, but now using a velocity time graph. Suppose the reaction time is 0.8 seconds and, during this time, the speed does not change. Braking takes another 3.2 seconds and, after a total of 4 seconds, the car comes to a stop. How can we determine the stopping distance of this car? Well, by figuring out the reaction distance and the braking distance first. The reaction distance is the area underneath this part of the graph, which is a rectangle. And in this case, that is equal to 20 times 0.8, which is 16 meters. And how about the braking distance? Well, the braking distance is equal to the area of this triangle, which is 1/2 times 20 times 3.2. And coincidentally, this also equals 16 meters. And that means that the total stopping distance is equal to the reaction distance, which was 60 meters, plus the braking distance, which was also 60 meters. So the stopping distance is equal to 32 meters. And that's it. To conclude, now you know that negative acceleration is called deceleration. You know how reaction distance depends on reaction time, and you know how to determine the reaction distance, braking distance, and the stopping distance from a velocity time graph. And that's it. That wraps up Chapter 5, Forces in Motion. I hope you enjoyed watching these videos and that they were helpful. For me, it would be really helpful if you leave a comment down below. Anyway, thanks for watching.